Okay, today let's have a look at the last two sections of chapter 3. In this lesson, we'll talk about atomic structure and the periodic table, and then applications of quantum mechanics. As the study of chemistry progressed from the 17th through the 19th centuries, it had become evident to scientists that Earth is composed of a great many elements, each with very different properties. Scientists realized that the structure of matter is much more complicated than the simple model of earth, air, fire, and water suggested by the ancient philosophers. As more elements were separated and identified, chemists learned about their properties. Gradually, chemists began to notice patterns in the properties of elements. So, have you ever wondered why elements in the periodic table are arranged the way they are? The elements of the periodic table are arranged according to the way electrons arrange themselves around the nuclei of atoms. Electron arrangement determines the chemical behavior of every element. After this section, you should be able to look at the position of an element in the periodic table and predict this electron arrangement. You will also be able to apply the quantum mechanical model of the atom to explain the periodicity of chemical properties. Understanding how electrons are arranged in atoms has allowed engineers to make new products and develop new technologies. For example, lithium, which is shown here in figure 1a, is a very reactive element found in group 1 of the periodic table. Lithium's reactivity is due to the arrangement of its electrons and their location relative to its nucleus. When the lithium is exposed to water, it reacts noticeably. You can see this shown here in figure 1b. Scientists have learned to maximize the potential of lithium by using it in batteries for cell phones, MP3 players, laptop computers, radios, cameras, pacemakers, hybrid and electric cars, and many other devices. So the lithium battery is illustrated in figure 1c here. The Bohr-Rutherford model of the atom provides only a limited explanation of how electrons are configured in an atom. Bohr-Rutherford diagrams are useful for the first 20 elements up to calcium. The quantum mechanical atom model, with its 4 quantum numbers, not only describes all atoms in the periodic table, but also allows us to make theoretical predictions about atoms and their chemical properties. To see how quantum mechanical model applies to multi-electronic atoms, which means atoms with more than one electron, we can consider helium, which has 2 protons in each nucleus and 2 electrons in the 1s orbital. So 3 energy contributions must be considered in the description of the helium atom. First, the kinetic energy of the electrons as they move about the nucleus. Second, the potential energy of attraction between nucleus and the electrons. And third, the potential energy of repulsion between the 2 electrons. Even though the helium atom could be described in terms of the quantum mechanical model, the Schrödinger wave equation cannot be solved because the repulsions between electrons cannot be calculated exactly. This problem is called the electron correlation problem. The electron correlation problem occurs with all multi-electronic atoms. We'll treat these systems using the quantum mechanical model it's necessary to make approximations. The most common approximation is to treat each electron as if it were moving in a field of charge. That is the net result of the nuclear attraction and the average repulsions of all the other electrons. For example, a sodium atom has 11 electrons, right? 10 electrons in the first and second energy shells, and 1 electron in the third shell. And this concept is illustrated here in figure 2. Now consider a single outermost electron and the forces acting on it. The outermost electron is attracted to the positively charged nucleus, but is also repelled by the 10 electrons in the first and secondary energy shells. The net effect is that the outer electron is not bound to the nucleus as tightly as it would be if the other electrons were not present. In essence, it's screened or shielded from the nuclear charge by the repulsions of the other electrons. The orbitals of multi-electronic atoms have the same general shapes as orbitals for hydrogen, but their sizes and energy values are different. These differences occur because of the interplay between the nuclear attraction and the repulsions from the other electrons. One important difference between multi-electronic atoms and hydrogen atom is that for hydrogen atom, all the orbitals of a given principal quantum level or shell have the same energy. For example, in a hydrogen atom, electrons in the 2s and 2p orbitals possesses the same energy. In the multi-electronic atoms for a given principal quantum level n, the energies of electrons in the different orbitals vary as follows. Usually we'll have ENS is less than ENP, less than END, less than ENF, which is shown here in bottom left. In other words, electrons in a particular quantum shell fill orbitals in order of increasing energy, S, P, D, and then F. The reason for this has to do with the probability density of these orbitals. For example, notice that in figure 3 that electron in the 2p orbital has its maximum probability closer to the nucleus than does the electron in the 2s orbital. You might predict that the 2p orbital electron has lower energy than the 2s orbital electron. However, notice that the small increase in electron density that occurs in the 2s orbital very near the nucleus. This means that for a small but very significant time, the 2s electron is closer to the nucleus than the 2p electron. This effect, called penetration, causes an electron of a 2s orbital to be attracted to the nucleus more strongly than an electron of a 2p orbital. Well, to summarize, electrons in the 2s orbital possesses less energy than electrons in the 2p orbital of a multi-electronic atom. The probability distribution can also be represented by the probability profiles shown here in figure 4. The same rule applies to the other principal quantum levels. The relative energies of the electrons in n equals 3 orbitals are E3s less than E3p less than E3d, for example. In general, the more effectively electrons of an orbital penetrate the shielding electrons, the lower the energy of the electrons in that orbital. And here, the relative energies of the orbitals of the various sublevels are shown in figure 5. You can have a look at that by yourself. Also note that each orbital or dot here can contain up to 2 electrons. Okay, next let's have a look at the off-ball principle and writing electron configurations. We can apply the quantum mechanical model to show how the electron arrangements in items in the ground state account for the organization of the periodic table. The location and number of electrons in the energy levels of atom or ion is called electron configuration. As we move across a row of the periodic table from left to right, items are arranged in order of increasing atomic number, or proton number. Note that in a neutron atom, the atomic number is also equal to the number of electrons. The result is that as you move across the periodic table from the left to right, the electron number of the elements also increases, right? The electron configuration of an atom can be determined using Aufbau principle, which hypothesized that the atom is built up by progressively adding electrons. Furthermore, it states that as electrons are added, they assume their most stable condition, or energy orbital, by filling the lowest available energy orbitals before filling higher energy orbitals. So here figure 6 shows how an Aufbau diagram can be used as a tool of determining the electron configuration of an atom. The word Aufbau is a German for building up. So I'll give you some time to have a look at the Aufbau diagram here. Probably you want to write this on your notebook. Okay, we're going to use this diagram a lot in the following discussion. Okay, the Aufbau principle can be demonstrated by examining the electron configuration of the elements, moving from left to right along the periodic table. So let's have a look at some examples here. The hydrogen atom has one electron, right, which occupies the 1s orbital in its ground state. The electron configuration for hydrogen is written as 1s1. So apparently the if the subscript of s, if the subscript is 1 here, sometimes you can also omit the subscript 1 here. Just write 1s, that's also okay. And this can be represented by the following energy level diagram or orbital diagram, in which we put a upward arrow here in the 1s orbital because it only contains one electron here, right? And next, let's have a look at the next element, helium, which has 2 electrons, right? So according to the Pauli exclusion principle, since the 2 electrons with opposite spins can occupy an orbital, the electrons in helium are in the 1s orbital with opposite spins. Helium therefore has 1s2 configuration. Okay. Next, the atom of the element lithium has 3 electrons, right? 2 of which can go into the 1s orbital, which is now full. Then the 3rd electron occupies the next lowest energy orbital, which means n equals 2, the 2s orbital. So lithium has 1s2, 1s1 configuration here. Did you get it? And the atom of the next element, beryllium, has 4 electrons, which occupies of 1s and 2s orbitals, which is illustrated here. And next one is boron. Boron atom has 5 electrons, 4 of which occupies 1s and 2s orbitals. Then the 5th electron goes into the 2nd type of orbital with n equals 2, right? Namely the 2p orbital. So all the electrons in the 2p orbitals have the same energy. So it does not matter which 2p orbital the fifth electron occupies. By convention, we write it in the left-hand orbital. So you might want to know how we can fill the electron configurations for the next element, which is carbon, right? So let's have a look at another rule we need to follow when to fill electrons in the next element. For an atom with unfilled orbitals, the most stable energy level, or the lowest energy, is achieved when electrons occupy separate orbitals with parallel spins. An atom of carbon, the next element, has 6 electrons, right? 2 electrons occupy the 1s orbital, 2 electrons occupy the 2s orbital, and 2 electrons occupy the 2p orbital. So the problem is, shall we write them in one of the 2p orbitals but with different directions, or shall we write them in parallel like this, right? Since there are 3 2p orbitals with the same energy, the electrons occupy separate 2p orbitals. This configuration is summarized by the Haas rule, which states that in a particular set of orbitals that have the same energy, the lowest energy configuration for an atom is the one with the maximum number of unpaired electrons allowed by the Pauli exclusion principle. In simple terms, this means that before any 2 electrons occupy an orbital in a subshell, other orbitals in the same subshell must first each contain 1 electron. Electrons filling a subshell will have parallel spin before the shell starts filling up, with electrons have the electron configuration for the carbon atom could be written as 1s2, 2s2, 2px1, 2py1 to indicate that the electrons occupy separate 2p orbitals. However, the configuration is usually written as 1s2, 2s2, 2p2, and it is understood that electrons are different 2p orbitals. The energy level diagram for carbon is illustrated on the diagram on the right. Note that the unpaired electrons in the 2p orbitals are shown with parallel spins. The higher energy orbitals have some anomalies in the order of filling orbitals. For example, if you observe this diagram here, the energy of the 4s orbital is lower than the energy of the 3d orbital, right? Therefore, the 4s orbital must be filled before the 3d orbitals. When building the electron configuration of atoms, it's important to strictly follow this order, which is illustrated here. Four S is before 3D. So use an off-bar diagram, which is the diagram on the left, to write electron configurations in order of increasing energy. To do this, you will also need to know the number of orbitals in each type of subshell. Just note that S equals 1, P equals 3, D equals 5, and F equals 7. That's the number of orbitals in each type of the subshell, right? When you have an S, you have just one orbital. When you have a P subshell, there are 3 orbitals. When you have a D subshell, there are 5 orbitals. When you have a F subshell, there exist 7 different orbitals. Okay, so let's make a summary here. This is a procedure for writing an electron configuration. First, use the periodic table to determine the number of electrons in the atom or ion. Second, assign electrons by main energy level and then by sublevel using an energy level diagram or an alphabet diagram. Then distribute electrons into orbitals that have the same energy according to Haas rule. Last, for each sublevel before starting with the next sublevel, continue until all the electrons are assigned. For anions or negatively charged ions, add an appropriate number of additional electrons. For cations, or positively charged ions, remove an appropriate number of electrons. So following this procedure, we can easily see the electron configuration for the next few elements. The electron configuration for the nitrogen atom, which contains 7 electrons, is 1s2, 2s2, and 2p3, right? Note that the 3 electrons in the 2p orbitals occupy separate orbitals with parallel spins. And the configuration for the oxygen atom, which has 8 electrons, is 1s2, 2s2, 2p4. Note that one of the 2p orbitals is now occupied by a pair of electrons with opposite spins, as required by the Pauli exclusion principle. And next, the energy level diagrams and electron configurations for items of the elements fluorine, which contains 9 electrons, and neon, which contains 10 electrons, are done as follows, right? For neon, the orbitals n equals 1 and n equals 2 are now completely filled. In items of sodium, the first 10 electrons occupy the 1s, 2s, and 2p orbitals. So the 11th electron must occupy the first orbital with n equals 3, right? The 3 orbital. The electron configuration for sodium items is 1s2, 2s2, 2p6, 3s1. To avoid writing the increasing string of inner level electrons, a shorthand using noble gas configurations is used here. So in this abbreviated form of electron configuration, the nearest noble gas preceding the element is noted in brackets, and the electron configuration is continued from that point forward. So for example, the noble gas configuration for sodium is, well, we need to write neon in the brackets first, followed by 3s1. Right? You can see the shorthand notation here. So the electron configuration of sodium is either this one here or the shorthand one here, where the bracket neon represents the electron configuration for neon, which is 1s2, 2s2, 2p6. Did you get it? These are the 2 ways you can write electron configurations for an item like sodium. Okay, do you have any questions? If not, let's have a look at some sample problems to check your understanding so far. Okay. Okay, let's. Oh, before we do that, let's have a look at the item of the next element, magnesium, which has electron configuration 1s2, 2s2, 2p6, 3s2, or neon followed by 3s2, right? Items with the next elements, aluminum through argon, have configurations obtained by filling the 3p orbitals one electron at a time, which is shown here in this figure. You can, well, if you use a detailed periodic table, electron configurations are illustrated on the second row to the last. Alright, if you don't have any questions, let's have a look at a sample problem here. Can you write the full electron configuration for sulfur item, which is denoted by S, right? So you can use your periodic table to locate location of sulfur. First, you need to find its total number of electrons in that atom. In the item, how many electrons in the item? Alright, let's have a look at the solution together. So step 1 is to determine the total number of electrons in that atom, right? Sulfur has 16 electrons. Then assign electrons in order of main energy levels and sublevels using the Aufbau principle. Remember that each orbital can hold 2 electrons, and the various subshells have specific numbers of orbitals. There is 1s, 3p, 5d, and so on. One s has 2 electrons, 2s has 2 electrons, 2p has 6 electrons, 3s has 2 electrons, and 3p orbital will fill 4 out of the 6 orbitals, right? So the electron configuration, or the full electron configuration for sulfur, is 1s2, 2s2, 2p6, 3s2, and 3p4. That's the full configuration. The question asks to find full configuration, right? So do not use any abbreviations here. Although we know in the periodic table, it's usually written as neon followed by 3s2, 3p4. Are you clear? Okay, let's have a look at another problem. Identify the element that has items with the following electron configuration. So if you are given a item, you should be able to find its electron configuration, right? You should also be able to find the element given its electron configuration. The reverse process is much simpler, right? You can just count the number of electrons actually. So if you add these numbers up, 2 plus 2 plus 6, plus 2 plus 6, plus 2 plus 8, then it's not very hard to find there are 28 electrons, right? So the atomic number of this element is 28. Then look up your periodic table. The number of electrons corresponds to the number of protons in the neutral item. Therefore, the number of protons is 28. So the element is nickel, right? Are you clear? Okay, let's have a look at another one. Write the shorthand electron configuration or noble gas configuration for the chlorine atom. So I'll show you the periodic table here. You need to find the location of the chlorine, right? So what is the atomic number of chlorine? Chlorine is here, right? Its atomic number 17. So in the neutral atom there are 17 electrons, right? Then are you able to write its electron configuration? Alright, let's have a look at the solution. So first, you need to determine the noble gas immediately preceding chlorine, right? Which is neon and E. Then add the additional electrons to this noble gas. So the shorthand electron configuration for chlorine is Ne followed by 3s2 and 3p5. Are you clear? Okay, last, let's have a look at a sample problem, which is about electron configurations for ions. Can you write the electron configuration for calcium ion? Alright, let's have a look at the solution. So follow the same processes as you did for a neutral item, but we need to add or remove electrons as required for ions, right? So first of all, the electron configuration for a calcium atom is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, right? The calcium ion has a +2 charge. That means we need to remove 2 electrons. So the configuration for the calcium ion is 1s2, 2s2, 2p6, 3s2, 3p6. Did you get it? Okay, so in this lesson we have learned some general rules to determine the electron configurations, giving the name of the element, right? Of course, there are some exceptions. So in the next lesson, we'll have a look at some exceptions, and also have a look at the explanation of the periodic table. So we'll leave this to the next class. So today's class is over, and I'll see you next time. Bye.